Hey, what's going on, guys? Games here. In this video we'll learn how to reference a certain variable located at a certain actual physical address in the random access memory. But here is the trick. So if we say if we take an assembly file like this shell.asm, and let's say I want to call the variable like this, like intro. Okay, we can just use the variable name. That's pretty it. Very simple. And here we have this intro variable. But literally, what intro is it's the certain address based on the offset from where the shell is loaded into the random access memory, and then we just have the addresses for these instructions, and then later on, eventually, we come to this exact place. And this is actually the place in the memory. And once we've loaded our shell, let's say, into the memory, we can easily reference this variable by name. And this works perfectly well until we are within the territory of our file. And let's say even if we exhaust the 512 bytes here, which is not allowed in our operating system, but anyway, in that case, we would still be capable of referencing those variables that would be beyond the 512 bytes, or it's better to say like above the 512 bytes in terms of the address is growing, right? So potentially, if let's just have a look at the memory map that we have here. So we have the shell loaded at this address. So let's say if the files were somewhere here, and I have defined what we have in the files, like this stuff, not in the separate file, but if I have defined this, say here in the same file, in that case we could have still be capable of using the variable names. However, I decided to make a separate file for the files, and apart that, another thing to consider, a very important thing to bear in mind, is the files are loaded before the shell. So it's just the next 512 sector after the bootloader, where the bootloader lives. Okay, so now the question that we would be answering within this video is, how on earth can we actually reference the variables within this range? Okay, so literally we're going to be referencing these variables, and note that these variables are just the plain by definition. They don't even have the labels, because we can't use that labels because we're not linking this assembly files together, because I really want to be them kind of separate. Okay, so how can we do that? That's what this video is dedicated to. So we can reference by the actual physical address. So that's how we're going to be doing it. Okay, so but before I will show you how this works, we need to make a bit of a conventions on how this list is going to be operating, and here it is. So the problem is the following. So if we have a different size, a different number of bytes for every file being said here, well, here it's the same number of bytes, right? But the game might have more or less characters to store its name, and in that case, the offset between like the offset for every next element is not going to be fixed, right? So here we have the so this variable starts at offset 0 at the segment where it is, and that's the actual location in memory is 7E00. Okay, so at 7E00 we can find this one, but in order to find this one we need to say 7E00 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, and 21. So here, so the address of this Tetris would be 7E00 plus 21, and the offset for bricks would be 7E00 plus 21 plus 1, 2, 3, 4, 5, 6, 7, 6, and 7 and so on. So it's not really handy, and encoding this like that would be a real pain. Hence the idea to have the equal number of characters of bytes to encode a single file name comes onto the stage. So we're going to be using this. I'm not sure whether it was exactly only 8 characters long names in DOS operating system in MS-DOS. I don't remember whether this was the case or not, but we're going to be using this exactly 8 bits to store the stuff. So the very first one will take the snake. Okay, then we will have our magnificent Tetros, and then the game that we'll be working with is called Bricks. So Bricks and Tetros are the same size, but Snake is not. So these are the games that I've actually already managed to connect to the GameOS, so that's the reason why I'm using these exact games. Okay, so these are the exact games that authors gave those games to reference them, so I just keep them as is. And now I want every line to be exactly 8 bytes long, so let's calculate. So 1, 2, 3, 4, 5, 6, 7, 8. Now here 1, 2, 3, 4, 5, 6, 7, 8, and respectively here we have the same thing. Okay, just get rid of the trailing spaces, right? Okay, save. So the next step, and now we know that the offset for a next file is going to be equal to 8 bytes. So 7E00 is the address of where the snake lives, and then Tetris would be 7E00 plus 8, and the bricks would be 7E00 plus 16. And now let's actually see how this is going to be working on the real deal to make it more clear. Okay, so before anything else, let's actually clean up the code from the previous episode. So just want to open terminal here. All right, and currently it should be showing whether the string match or not. That's the material from the previous tutorial. Yeah, we got string match, perfect. So I no longer need the code for this test routine here. Okay, but here we're not going to be enabling the loop still, so we just rename the test routine to someone else. Okay, so routine to test to reference variables from RAM, from physical RAM location. And by the way, what the variable is essentially is a shortcut, a name that's literally a replacement for an address that we have in the random access memory. So here we would be kind of handcrafting the variables on our own. So I'll use the define directive to do this for me. Okay, so another little thing. So yeah, before I forget, guys, just in the compare strings, I want to point di to the user input where it would eventually gonna be pointing to, and as I point to AX, because AX is gonna be so if you think from the high-level programming perspective, AX would be something like an argument sent to the function. We can think of that roughly as like that. Okay, so just to not get in bother with this later on. And also I don't need this temp variables. Yeah, I don't need this temp variables anymore, so I can get rid of them. Okay, and yeah, so we still have our print string available, right? And now it should, so let's just stuck in the infinite loop, and now it simply should do nothing. Okay, yeah, by the way, yeah, let's see if I didn't break anything and the shell is kind of still working, and we can also delete the files. Yeah, great. So yeah, stuck in the infinite loop. All right, and now again, like, so the address is for our files is starts from 7E00. So this is how we can make use of it. So if I say move SI7 hexadecimal hexadecimal 7E00. So what we do here, SI points to snake, well, actually to the S to be exact. So let's make it like points to, oh man, okay, it was better. Points to the address of S character in snake string located in files.asm. Okay, hope it's clear. And since we have initialized the source SI, which stands for source index, since we have initialized the source index pointer, we now should be capable of printing whatever we have there. So from here and up to the 0 terminating characters. So we should be able to print word snake from this exact memory location of 7E00. Okay, so call print string. Okay, and I just want to run this again, and here we go, we get a snake. Awesome. Now the next logical question is of how to print the name of the next game. So let's say we would probably want to have a command to print all of the games. And yeah, by the way, guys, this might be a good idea to implement that function in this video. Yeah, because otherwise there would be just too less material, not enough material apparently. Yeah, this is a good idea because we will want to type like, I don't know, list to get all the files that we have. So that makes sense. That makes perfect sense. Why didn't I think about this before? I don't even know. Okay, but so print first file from files.asm. Okay, and now to print the second file, we can say move SI and hexadecimal 7E00 plus 8, because that's the exact offset in bytes that we want to have there, right? So that's pretty it. Okay, so here SI points to T of the tetros, points address of T in tetros string located in files ASM, and here call print string. Here we print the second file. Print the second file, and now we should be capable of seeing tetros along with the snake. Okay, but we didn't print a new line character, which is okay. Yeah, yeah. And by the way, well, we could have. I'm just wondering. So should we have the new line being encoded? Yeah, probably in order to avoid polluting the files ASM, I can. Okay, guys, another little improvement. So messages, variables. So let's call it a new line and define bytes. So 10 for a new line, enter, like the new line character, and 13 for carriage return. Save, and here we can also print the new line in between. So let's say move SI new line called print string. So now this should print it by, okay, why didn't print? They have an error. Oh, call. Oh, what have I done? Oh, I'm sorry guys, what have I done? Nope. Should be here. Okay. I have a warning. Oh, sorry guys, need to fix this. So 100s. Oh, next byte. Yeah, it was working even like that, but yeah. Yeah, okay, no warnings now. Great. Okay, so here, let's say move to SI. I want to move the new line and call print string. And here we go. We got like files been printed one after another, which is good. All right. So now, yeah, I just want to encode these values. So in order to avoid using bare addresses, but use like variables instead. So copy 7E00. So here I can say that I want to define let's call it files, and hold on a sec, we have the files address already. We have the files address already, so we can use that files address instead. Files address. Okay, this should give exactly the same output. Great. So the only thing to encode is this offset a file. So let's call it define file address offset being equal to 8, and so this is the size of a file name. Size of the file name, that's pretty it. Okay, and here I can now say file address plus file address offset. Yeah, I don't really like that. Okay, just put them somewhere here. I really like when the commentaries are all within the same. Maybe call it just file offset. Or let's call it file name size. File name size 8. Okay. File name size. Oh, it still doesn't match. Name size, yeah, name size matches perfectly well. Well, it might not be. Maybe name offset. I'm sorry guys, I'm probably doing some weird thing, but name offset. Okay. Hold on a sec, I just need to figure out what would be the better name for a variable. Okay, let it be just the offset, and yeah, so size of a file name, and I just call it offset. That's pretty it. I don't want this long names for variables. So the offset is the size of the file name. Okay, and offset, and just offset here, and this is it. Great. So, all right. Yeah, we got it. Perfect. So then what? And if we want, say, to reference somewhat different, like this one, so here we have the two offsets. So we can simply say like 2 multiplied by the offset, and run shell, and we have snake and then breaks. Awesome. So I hope it's clear. Yeah, let's I don't know, I want to keep this code as didactic as possible. So yeah, first I just keep this routine without going into the main shell loop, and then I'll write a procedure to print all the files that we have, right? And then what we're going to be doing then, yeah, and then we just call that procedure right over in here. Okay, so yeah, so here si points to new line variable, this file, and just print the new line. It's pretty simple. And copy, paste, 2 multiplied by the offset, points to B, and breaks, string located in file ISM, print third file name, basically, not the file, second file name, first file name, and this is it. Okay, sorry. So let's have a look what we got. Okay, and we didn't specify this. We didn't specify the new line. So let's do this. But you see, like, it would have been much easier doing this in the loop, but I just want to make things crystal clear. So yeah, here we go. Okay. All right. Okay, so now let's create a procedure called, so read sector, print string, execute, compare strings. Let's put it here. So we want to print all files available. Available on storage device, on USB, flash drive in our case. So let's call it print files. Okay, and yeah, now we need to somehow know when to stop the loop over the files. So yeah, we need to, okay guys, let's define a few more variables. So let's create a variable called no file, and it would be equal to, I'm sorry, just define word in this case. This is important, so I'm using define word, not the define byte, and it's going to be equal to 0, and then the file list is going to be equal to, like, define word. And now we need to all the files should now be listed here. So I want to list, so starting from the file address, so file address, and then file address plus offset, and then file address plus 2 multiplied by the offset. And in case if you will want to add new files to be able to run them on this operating system, you will need to do this manually here, just multiplied by 3, 4. I don't know, maybe one day it would be making some sense to actually doing this automatically in a loop somehow, but yeah, I don't know, I wasn't preparing for this yet, so for now I just leave it as is. And now it also should be possible to if I just want to check one little thing, guys. So if here I say file list, it should be printing the same Tetros break. Oh, it didn't print this. Oh, whoa. Oh, that's because, hold on a sec. That's because I should do like this, the content of the file list. Okay. And now here, let's say the content of the file list, the content of the file list plus, I guess, 4 bytes, right? Because we define the words there, not the bytes. Yeah, but hold on a sec, nope. Tetros didn't work. Is breaks the second? No, it's the third one. Oh no, we still need to add 2. I'm sorry. Yeah, still we need to add. Still need. Yeah, I'm sorry, guys. Just adding 2 is enough because that's the content of the file list, not yeah. Okay, and here respectively, we can say file list plus 4. File list plus 4. Okay. And now we should be able to see all the rest of the guys. Okay, great. Okay, so we need a counter to hold these values, like +2, +4. Okay. And what else? So we're gonna I'm gonna be using the BX register for that purpose because that's how I was doing within the search game routine. So okay, print files. So let's say move BX 0. So this is the counter. So reset game counter. So BX serves as the game counter. And then let's make enable next game. Okay, and here jump to next let's call it next file name. Let's call it next file. Jump next file. Save. So here process next file name, literally print, but yeah. Okay, so also we need to say add bx2, so point bx to the next file name. Okay. And for every so the print stuff, the most essential one, so this one, file list, yeah, copying, most essential, so we need to initialize si with a file list plus bx starting from 0. Okay, so si points to address of the first character of the current file name located in files ASM. Good. And print current file name. Okay, so SI points to the address. Oh my god, guys, I feel like I would need to. Yeah, I'm sorry for this, but for me, this is very essential to have exactly the same offsets all the way. Sorry for wasting your time for this, but for me, this is very important, really. But okay, I can do this. Okay, I can do this in my spare time. All right, so yeah, let's go to the point. It just takes a bit too long. Okay, so this is it, and print string. So this should be printing. And also if it happens that there is no more games, so literally if bx is gonna be, or hold on a sec. Okay, I just remember why I've been using AX to initialize the file name instead of directly initializing the SI. I'm sorry guys. So let's say move AX and this thing, and we initialize the SI with the AX. So here AX points to the address, and here SI points respectively. Okay, and now the condition. So I want to compare the AX with a no game, or no file. Sorry, it's probably called no file, is it? No file, yeah, and we need to add no file here. So if it's equal to no file, which is 0, in that case we're done. Okay. If no more files left in the list, so jump equals to return. Just return then. Okay, jump next file, and here return, and return. And I think we can even do this like so. Return from the procedure. All right. Okay. Well, I'm not sure if I did everything properly though, because I wasn't preparing this file. Usually I have the file being prepared already, but I've been live coding this. So I'm not sure whether it works from the first run or not, but let me try. So I just want to comment out this stuff. I'm not going to be deleting this for now, so you could play around and figure out how things works. And instead I just want to say call print files, and if I did everything properly, so here want print all files available. All right, so if I did everything properly, it now should print all the files, but in a loop. Oh my god, it didn't. There's probably some errors. Instruction inspected 108. Oh, sorry. Okay, Snake Tetros bricks, perfect. And the only thing that we lack here is the new line character, so let's quickly fix that. So after printing the string, we also want to say move SI and the new line SI points to So string to print literally, and call print string. So here we want to print new line, and that's it. All right, and here we go. Perfect, guys. So we just printed all the files we have, right? We've printed all the files we have in a loop, which is pretty awesome, right? So yeah, and from now on we can actually hopefully we can finally go for searching the files and using our compare string routine to answer the question if we actually did manage to find if the file exists, if the user did input the file name that corresponds to the file that exists or not. Okay, and probably one last thing, just from the curiosity perspective, I want to have a look at, so let's not erase the shell bin. No, we want to cat it but not erase. Okay, now to erase the shell bin, I just want to see how many free bytes within this 512 bytes are still available. Control F and now ls. So there should be shell bin, and let's have a look. xxd shell.bin. So how many free space? Okay, we have a plenty amount of bits still being available for us. Yeah, and this should be fairly enough to write a routine, actually the search routine. Okay guys, so this is it from my side. I hope you learned something interesting out of this tutorial. So see you in the next one. Until then, and take care.